Okay, so as we start with chapter 4, mechanical oscillations, the first step we're gonna do in this chapter is math requisites. Before we start with the physics of this chapter, we need to stop a bit and solve some of the mathematical problems that we might encounter. After that, we can continue and start solving regularly. Okay? The first thing we're gonna cover in mathematics is some basics about trigonometric functions. A circular function, or also known as a sinusoidal function, is simply a trigonometric function which is characterized by symmetry and periodicity. The general form of such functions is usually y equal a sine 2 pi over t0 x plus b, or a cosine. We can always replace the sine by cosine without any changes. Now, 2 pi over t0 has some name, b has a specific name, and a as well. Nevertheless, sine or cosine are gonna give the same result of periodicity. A is called the amplitude of this graph, which is wave-like. T0 is the periodicity of the function. It is like the period which we know in physics. Nevertheless, in mathematics, the interval on x in which a function repeats itself is referred to as periodicity. B is a constant which contributes for the y-intercept. Notice that when x equals to 0, y equals a sine b. So when x equals to 0, y equals a sine b. You notice sine b. Okay, so b contributes for the y-intercept, for the point where the graph or the function cuts the y-axis. Now, 2 period or 2 pi over the period is called the angular frequency. It is like the frequency which we know in physics, but since it is in mathematics and it is 2 pi over the period, not 1 over period, we call it angular frequency. Some particular trigonometric functions can be seen here. Over here, the graph in red is simply a sinusoidal function having an amplitude of almost 3, if you can make up this number. And notice it's also minus 3 from below, so it's symmetric. It has periodicity from here to here, which I can read around 6.2. This graph here, shown in blue, has the same amplitude, but periodicity of around 3.1. This graph as well has a different y-intercept. Notice the y-intercept differs here. Now, passing to something which is a bit more complicated about circular functions. First, we start with the derivatives. The derivative of a circular function are also circular. That's something which is for sure. Now, if you have the function sine x, its derivative is cosine. While if you are deriving the function cosine x, you get minus sine. A good note that you can always refer to in order to relate these derivatives together. Always consider this circle, the trigonometric circle, in which we know that the x-axis is the axis of cosines, so here is the cosine, and the y-axis is the axis of sine. When we move clockwise, we derive, or when we derive, we move clockwise. So deriving sine, you get cosine, while deriving cosine, you get minus sine. To generalize this, in general, the derivative of sine u is always cosine u. But we need to add the penalty thing, which is the direct derivative of u with respect to x. We can also use the Lagrange notation, in which we say d sine by dx equals cosine multiplied by du by dx. Don't forget that du by dx is nothing but u prime itself. The same thing for cosine u, which is minus u prime times sine u. So each time you derive sine or cosine, you have to derive on two levels or over two steps. First, sine becomes cosine, cosine becomes minus sine, and the second step is the direct derivative for whatever is inside the trigonometric function that you're studying. Passing to the second idea, which is also a bit complicated, trigonometric relations. These are simply a set of relations that we learned in whenever we need to deal with some trigonometric transformations. Some of these transformations are useful, and especially when we are given a certain angle and we need to find some other angles related to it. For example, if you know sine and cosine of x, and you want to find sine of x plus pi over 2, we know that sine x plus pi over 2 is cosine x. We know that cosine x plus pi over 2 is minus sine x. Same thing for minus x. So if an angle is pi over 2 plus x, let's say x is here, okay, and this is x as well, okay? So the relation between this angle and this angle is simply found here. Now, we don't need to memorize these. If we are in need of them, we can simply refer to this paper and use them. On the other hand, if you are given two angles A and B and you need to find sine or cosine of A plus B, cosine A plus B is cosine A cosine B minus sine A sine B. Sine of A plus B is sine A cosine B plus cosine A sine B. Again, don't memorize these equations. We have seen them in previous classes and they might be useful right now. Right now, to make sure that you got this point, solve this application, math checkpoint 1, in which you are given a circular function y equals 4 sine 2x plus pi over 2. Indicate the amplitude, the angular frequency, and the period or periodicity of f of x. Then determine dy by dx, or simply y prime. As we always say, at the end, we're gonna just post a video in which we have solutions of all these applications, and in this case, of all these checkpoints. The second application, Math Checkpoint 2, deals with the trigonometric relations, the ones we mentioned at the end, in which we have sine pi over 2 plus alpha, sine minus alpha, or sine a plus b, cosine a plus b. You don't need to memorize these relations. You can place them right now in front of you and try to solve this activity. For example, when I have sine pi over 2 plus pi over 3, all I have to do is just search for the convenient equation that can help me determine this line. When you finish, you can check the video in which we solve the solutions and correct your work. Now, the last point that we need to focus on in mathematics is differential equations. Previously, we have discussed differential equations when we studied momentum. However, we studied differential equations in their simple form. For example, we have taken an equation which is y double prime equals to constant. The solution was back then y equals k over 2x squared. How was this generated? Let's step a bit back. If y double prime equals to k, then y prime, think of a function that upon deriving you get k, a constant. It is simply y equals k times x plus another constant, let's call it b. Now, think of a function y that upon deriving we get y prime, which is kx plus b. To derive something to get kx, it is simply half kx squared. The half comes from deriving x squared. If I derive x squared, I get 2x. Since y prime has kx and not 2k, simply I multiplied kx squared by half. Same thing for b, but b is easier here, plus bx plus a constant, let's call it c. So when the function is or when the derivative or the differential equation is, y double prime equals to k constant, we expect the solution to be y equals half kx squared. Okay? Now plus some other terms. The differential equation we're going to talk about right now is a differential equation of the form y double prime plus k squared y equal to 0. If I take this equation and convert it to y double prime equals to minus k squared y, I notice that I'm searching for a function that, upon deriving twice, it takes me back to the original function in the opposite way. When I hear myself repeating this, getting the same function with a minus, I remember when we studied the trigonometric functions at the beginning. When we derived them once and twice, we got the same function. So, Such a differential equation has a solution which is always sinusoidal. Y equals A sine kx plus B cosine kx. A and B are constants because you know trigonometric functions, whether they are sine or cosine, upon deriving twice, we get minus the original function. That's why we have written a combination of both sine or cosine. Now, using the trigonometric relations cosine A plus B, cosine A minus B, we can simply replace this function y equals A sine kx or plus B cosine by A sine kx plus B or simply A cosine kx plus B prime. Now, this is related to the trigonometric functions that we studied at the beginning. You notice the differential equation that we are interested with is the one that leads directly to a sinusoidal function, because I always keep that in mind and always remember also that our lesson is about oscillations. Trigonometric functions are oscillatory functions. So that's why we focus on them and we study everything related to them, even differential equations. Now, we finished all the requirements. As a first application on the differential equations that we mentioned at the end, y equals f of x verifies the differential equation y equal y double prime plus 16 over 25y equals to 0. Determine a and b if the solution is y equals 4 sine ax plus b. You are given the solution, you need to find the terms inside that solution. Try to think about it. Consider the differential equation y double prime plus 9y equal to 0. Determine the solution knowing that its curve passes through 0, 5 and the derivative as 0 is also 0. Okay? So try to think about this math checkpoint relying on what we have discussed in differential equations. The last application on mathematical requisites is an exercise including oscillations or trigonometric functions and differential equations at the same time. Consider a graph, which is shown on the right side, which is the representation of a function y equal a cosine ax plus b. This function also verifies the differential equation y double prime plus 0.36y equals to 0. Determine a, which appears in the function or in the equation. Then, using the graph, determine capital A, the amplitude, and B, which is the initial phase, knowing that A is positive, small a is positive. Now, try to think about this exercise and solve it. It is a general exercise about all the mathematical requisites that we need. Not only that, this is an excellent introduction to go into oscillations and start the physics behind oscillations without worrying about the mathematical part. By this, we have reached the end of the math section that we need. Now, go over the applications that we suggested. Once you finish, check the video which shows the solution in details of all these applications. After that, we are ready to start with the mechanical oscillations using the physics aspect and physics approach. Okay, let's move on and see you in the upcoming section.